We're doing antibiotics on livestock and we're arguing against. I'm Justin Chang.
I'm Chris Rosedale.
Okay.
Yep. So first about antibiotics. Antibiotics are for both humans and animals. Antibiotics are an antibacterial drug used to prevent or fight infections. As you can see by the picture, they're used a lot more in animals. The ethical aspects of antibiotics. Antibiotic usage on livestock has a major focus on growth and prevention rather than treatment, meaning antibiotics are taken for industry use rather than medical use. Continued usage of antibiotics have led to diseases becoming extremely resistant, causing zoonotic diseases to become more prevalent and for livestock to become less resistant. Slaughterhouse workers are exposed directly to resistant bacteria through feces or blood, causing more laborers to suffer medical diseases such as E. coli. Sociological impacts of antibiotic usage on livestock. More and more people request that antibiotic usage on livestock to lessen or stop entirely. Only in the US is antibiotic usage on livestock prevalent. Europe even banned the practice. Disease outbreaks that occurred due to antibiotic use on livestock. In the 1970s, Salmonella had seen an increase in poultry and eggs due to growing resistance to penicillin. In 1992 to 1993, E. coli had a massive outbreak in the U.S. and occurred in Washington, California, Idaho, and Nevada. Over 500 cases reported for E. coli, around 150 hospitalizations, and 4 deaths due to the outbreak. Here's some issues around antibiotic usage. The first is that the continued usage of antibiotics on livestock has led to bacterial diseases to increase in resistance. Number two, as antibiotics are being adapted against, new drugs must be developed which are costly. And number three, human health receives a major risk as antibiotics are shared between livestock and humans, as are diseases. So the first issue, increased antibiotic resistance. Livestock are constantly treated with antibiotics to promote a productive industry, which leads to bacteria that are supposed to be killed by said antibiotic gain a resistance. Not all bacteria is killed during the drug process, meaning the remaining bacteria have learned or had a previous mutation to resist the drug. Resistant bacteria will reproduce and spread and will likely infect or even kill the livestock. Higher resistance renders previous antibiotic practically useless and creates a supergerm that puts livestock and eventually humans at risk.
To go further into how a bacteria gains resistance, drug resistance comes from spontaneous genetic mutation, meaning that only some bacteria will randomly, but will for sure resist an antibiotic. This is not controllable and it just happens in a bacteria colony. The resistant bacteria will survive and will reproduce, creating another family of resistant bacteria, thus rendering the antibiotic either useless or even harder, or you need more doses to get rid of the bacteria. 100% of bacteria colonies will never be treated, as it's very likely that even 0.1% of a colony will survive and begin to rebuild. This is equivalent to when you have a hand sanitizer and it only says 99.9 because it is right now medically impossible to completely wipe out bacteria. Bacteria specifically gain resistance using 5 different methods, and those 5 different methods are shown here. The first one is decreased cell permeability. This just means that the cell changes its membrane structure that denies the drug entrance to the cell. So essentially, it's just like a door that basically the cell just changes the lock on the door so the drug can't get it. For number two, it alters the drug binding site. And what this means is that even if the drug enters the cell, it needs to bind to the cell structure in general. But because of the door changing, it can't do that. So effectively, there's just a floating drug molecule inside the cell, and it's not going to be doing anything to the cell. Number three, the cell chemically modifies the drug. This just means that the cell basically either takes off or cleaves off a portion of the drug, or replaces parts of it, which again just turns the drug useless because now it's a completely different molecule that's not meant to destroy the cell, it's just now there. Another way, the fourth way, is active transport. The cell pumps out the drug by pumping in hydrogen ions, as a cell must exchange some component to gain a component. The theory here is that once the drug is in, even though it may not be cleaved off or might not be able to bind, the cell is still able to just essentially expunge the drug out using hydrogen ions. The fifth way is altering the pathway or the enzyme that the drug uses. And this is essentially just whenever the drug is entering, the cell just refixes the structure so the drug can't get in. Or if an enzyme is needed to connect to the drug, the cell will either cut off the enzyme or stop production or just straight up direct the drug somewhere else where there is no enzyme for it to use. To go further into our second issue, antibiotic usage is very costly. With bacteria becoming more resistant, more drugs are needed, or more need to be developed to counteract the bacteria. Essentially, what this means is that, again, you need more drugs just to fight the bacteria because now the bacteria is resistant. It might not be able to completely resist the drug, but now you're going to need more and more dosage. New drug development can be quite costly and ultimately proves to be in vain as the bacteria will just naturally resist the new drug. This is a very popular opinion in the medical community that the antibiotic usage or sanitization should be lessened because we are facilitating bacteria to become naturally resistant. And at some point, drug development will not be able to catch up to new bacteria, or the new bacteria will eventually just become completely something spontaneous, and the drug development will have to shift in a completely different direction, causing more research study or money to have to be put into that area. The livestock will also have to be replaced because if they do receive infections, which is very likely if the bacteria now resists the antibiotic, and if the bacteria manages to spread too far, the entire livestock may have to be replaced. And essentially, this is just really costly because now you're going to have to replace a cow for another cow, or maybe you have to replace an entire family of cows because now they have like E. coli inside them, or they're just way too infected to be even like used. And while you can medically process the meat, the risk is too high, and with restrictions from the FDA and uh, the meat industry being investigated by them constantly, it becomes a costly process because at many times they're going to have to replace the livestock. Issue number three is that human health is at risk. Now, what this means is that human health is essentially affected by the same bacteria that affects livestock. And another major issue is that antibiotics that are used among livestock commonly, like penicillin, macrolides, streptogramins, they're all used on livestock and humans. So, for instance, if salmonella will naturally resist penicillin, if it gains that resistance, and if a human were to get infected by that salmonella, say if it started off in a chicken and the chicken was exposed to salmonella and then they use antibiotics and then eventually salmonella that grew inside the chicken managed to reproduce and spread, if that chicken is now used for food and the human was able to contract it, the human will have to deal with a salmonella that is already good against penicillin. This essentially just means that treatment will be harder or more likely to fail, and it just makes it a much more difficult process just to get over a disease. Another major issue is that bacteria inside humans may even form colonies with other bacteria. So this might lead to the disease becoming mixed using antigenic shift, which just essentially creates a two disease in one combo, and human who is infected will suffer major consequences. Or it'll just simply create a supergerm, which now the supergerm is now resistant to certain antibiotics that would have killed it, and it also now just much more potent, which just puts more health at risk, and we don't want to create more diseases. And then the constant resistance adapting bacteria could eventually form an extremely dangerous disease. This is simply just means is that what if a salmonella, for instance, just continued to resist penicillin and it just kept going through people to people? This is how a pandemic or an epidemic forms. And like the SARS incident, now that humans are much more connected, they're going through planes and they're flying everywhere. This just means that we have created more risk to creating salmonella becoming the next Black Plague or the next influenza, next SARS. We're just creating the risk of it being even higher, and it's even worse if we can't treat it as fast, which would just make the bacteria spread even more. Another major issue that will be talked about later is that resistant bacteria can even spread the gene to other diseases. So say if, again, let's bring up E. coli. If E. coli has naturally resisted some kind of antibiotic, which is a very likely chance, the E. coli can actually spread it to another disease. Uh, let's say a type of food poisoning that could potentially grow worse because now that food poisoning bacteria could just adopt the resistant gene, meaning that human who's affected will now have E. coli and a stronger, more resistant food poisoning bacteria, which just makes it worse. And then this just essentially means that human health becomes at risk from a non-human source. This is something that we can control, but at the same time, we can't really control once it's in the process. We can stop it at step one, but we can't stop it at steps anytime in between until the end. And then resistant bacteria can spread the resistance genes. This essentially means in 3 different ways, bacteria can actually just spread its own DNA. And that DNA contains the mutation that allows the bacteria to be resistant. The first way is conjugation. This essentially just is cell-to-cell interaction. It's just when one cell basically connects to another using a tube with either of its hairs on the side, and both of the cells will literally just share the information, making the resistant gene go to the other, and they now both have the same genes. Another way is transformation. This is when a cell dies, it will actually leave behind its DNA, which can then be eaten or absorbed by another cell, and that same cell will eventually just take in the DNA, and the DNA will adapt to the new cell. So essentially, a dead resistant cell can pass on its DNA to a living non-resistant cell and turn it to a resistant cell. And this would be a problem again because now it would just make a non-resistant non-threat into a bigger threat. Transduction is the third way, and this is essentially transporting genetic material using a bacteriophage. And a bacteriophage is a virus that essentially infects a bacteria. What it does is it just goes inside them and corrupts them. Now, the bacteriophage is now just basically a combination of a virus and a bacteria. And say if a virus goes into a bacteria that's resistant, it now absorbs that genetic to make it resistant to drugs, making bacteriophage much more potent. And some major diseases are example of some of these transferable diseases that can become resistant due to antibiotic usage. Avian flu. So this is a flu adapted to birds, but can also go from person to person. The symptoms are that within 2 to 8 days, it can seem like a common flu, but then there's going to be cough, fever, sore throat, and eventually this can kill a human being, and we don't want this to grow any stronger than it is. Another major one is E. coli. Now, E. coli is an intestine infecting bacteria. People can get sick from this from eating contaminated water that has been exposed to species or food that has been, like, for example, E. coli inside a cow can fester, and if that cow is not treated well or the meat is not like completely purified, then it can go to humans, and it is a very life-threatening form of kidney failure. And on to our final opinions. Antibiotic usage on livestock is already a major problem here in the US due to the fact that it contributes to creating even stronger diseases. Bacteria has shown over and over to be extremely resilient, and this is due to the fact that it adapts so well to its situation. This adaptation will eventually create diseases that will be out of our control or cause temporary damage to our society by creating more outbreaks, creating stronger diseases that we can't deal with, or making treatment take even longer. And it makes it even worse because antibiotic used on livestock is used in humans as well. This means, again, treatment is less effective. So the salmonella that gains resistance to penicillin won't be affected by penicillin. So a human who needs penicillin will need much more dosage or might even need a completely different antibiotic. As it stands, even Europe has banned the use of antibiotics on livestock due to the danger it poses onto humanity. With how more connected the world is, creating stronger diseases could lead to catastrophic results. Overall, antibiotic usage on livestock could eventually create an extremely resilient strain of any foodborne illness and could cause some damage to humans or even create a brand new disease. That is our opinions against antibiotic usage.